All right, welcome back. Uh, so after last series of videos till building GPT from scratch, the plan was to move along and try to build GPT-2. But I took a detour and got interested in implementing a LSTM and recurrent neural network from scratch once, and then we'll move along to GPT-2. So let's go ahead and implement a simple RNN and LSTM models for a character level inputs and outputs. So our inputs, so our problem statement would be very same as what we are doing earlier in the series of generating names, wherein we generate a character or a letter one by one. And so most of the, so this is basically a architecture of RNN. We'll get back to this. So I'm starting with some preliminary code to prepare the data and get the batch of the data from previous videos. So it would look mostly the same. Load the names.txt file. List will get a list of names. We'll create vocabulary, which would be all the characters. We'll make the mappings string to character to index and index to character, and vocab size would be defined as the length of these mappings. We split the data words into two parts, train words and val words. 90% will be train and 10% will be validation. We define a few hyperparams: batch size, number of embeddings for number of embeddings and hidden dimension. So these would be used. Then we define a function of getBatch, which will take a split name, train or val or test, whatever, and a batch size as input. Um, it will initialize two empty lists, choose the data that we'll have to split, generate the batch from. Um, batch size uh, uh, indexes of length batch size are generated using this function within the range 0 to length of data minus 1, and we then generate a batch from the data starting at I, or basically index into the words list, get words at each of the indexes I and ix. And now for each of those words in the batch, we individually iterate and append a dot in the end, which is basically representing a end of a name, basically. Input output, again, empty list. We fill data into input output with a list of uh, basically this would be list of indexes corresponding to the ch1s that comes in this zip of chs and chs1. So this is a way in Python to iterate over consecutive elements, pair of consecutive elements. So if first, let's say if in the name Emma, if E is input, M will be the output. If M is input, M will be the output. If M is input, A will be the output. If A is input, the last dot that we append in the end, that will be the output. So that's how we iterate over a pair of inputs and outputs uh, using as a function. And for the first characters, uh, goes into the integers corresponding to first character goes into input list, and the integers corresponding to second character would go into the output list. Once we have these, we append them into our, so these would be of varying lengths, right? Every word will be of a different length, so these lists that come out of it, um, for different word here, would be of different length. So this basically input sequence would become a list of lists, where each element in this list input sequence would be of different length, varying lengths. So therefore we'll have to use pad sequence method, which comes from torch and then utils RNN. Pad sequence, what it does is, in a batch of data, it finds the longest length sequence, um, and as per longest length, it will pad all other um, entries in that batch basically to that longest length. So you have to pass in the input list, batch first equals to true, and padding value 0. For output sequence, we are padding it with -1, because when we are calculating loss using f dot cross entropy, we'll have to ignore the values where output is -1 to be included in loss calculation, because these are just padding for efficiency in forward pass, backward pass. We don't want them to be contributing to the loss. So we return these padded input sequence, output sequence. To show you one batch, uh, we call get batch once and print them. So we have defined batch size as 4, and yeah, batch size as 4. So you see every word here now looks, every sample in a batch. So this is basically the XP input batch, which has 4 samples, 1 sample, 2 sample, and so on. So one sample has lot of zeros padded in the end. The last sample has no zeros. This was the largest length list in that particular batch. So other samples were padded to equal that length, and correspondingly for this input, the output list would be this, wherein in the end you will have -1s padded. This 0 would be the end of every output, because we were adding a dot in the end, right? That is corresponding to 0 index in the string to index match, you see. So that's what 0 you will see here, ending for all of the outputs. So this is our input batch, this is our target batch. These are the indexes corresponding to the characters in that word, in those words. Now let's, uh, if you recall, this kind of modeling we have done with a count-based bigram model, where looking at one last character, we want to predict the next character by calculating probabilities from the counts of those bigrams. Then we did this modeling with a neural network and a neural network with some context size as input. We did all those now, and also, yeah, so character based language modeling we also did for the GPT kind of model, uh, where we did not predict names, but we tried to generate Shakespeare like text by having a block size, context length going in as input into the network with some attention scores, then some computations, etc. Now I was interested in implementing a simple RNN and LSTM for modeling this problem statement, where we um, generate names basically. So this is what a RNN architecture looks like. What happens is x1, x2, x3, xn are time steps, input at different time steps. So if Emma is our input, one input, E is x1, M is x2, M is x3, A is x4, then dot that we append in the end would be x5, so on. So these are different time steps inputs. H is hidden states of the cell. So this is basically RNN cell. So ideally the most common way of representing RNN is this kind of architecture cell, where you have RNN cell, you have inputs going xt, which is at different time steps. ht minus 1 is hidden state coming from t minus 1 time step, so last time step, and this RNN is generating ht, taking these two as inputs. We are generating current time step hidden state, and this hidden state goes back and back as input into the next time step. So this is a rolled version of it, and this ht basically is also used to make some predictions or some logits calculation out of it. So when you unroll that diagram, you get something like this, right? So x1 is input, h0 is output. You calculate h1 with some computation here. H1 is used to get the y1 logits, or based on problem statement, you can decide what y1 would look like, or even if you need y1 or not at all. X2, you get h1 as input. h2 would be computed and y2 would be computed with h2. So this is how it moves on time step by time step. And the basic idea is, in our previous modeling of neural networks or bigram counts, etc., we were not um taking in any information from the previous time steps for computing the next, predicting the next token basically. So based on current token, we are predicting next token, but we are not taking any information from the tokens further uh, back in the history. Now this is a way, although in attention mechanism based GPT-2 that we built, we were doing that to a large extent, to the best possible extent, by communicating between the tokens, forming a way of communication between the tokens. That was the best way possible these days. But this is an old approach, but was a very effective approach till a time. So I think we should understand this. So at any time step, it is not predicting y2 only on the basis of current input. It is also taking inputs from hidden state from previous steps, and subsequently h1 is having some information coming from h0 or any previous time steps. So ideally the way this should work is that um, all the previous time steps information is somehow accumulated at current time step, and it combines with the current input to give you the output that should be generated here. But there are a few problems obviously with it, of um not being able to maintain good amount of information from time steps way back in the history. So if the sequence length of this kind of network start getting large, they start to lose information very easily. Then there are some vanishing gradient and exploding gradient problems, which obviously, with if you let's say if you take a derivative of loss at this point with respect to h1, it would have um, chain rule implemented at each step, and all the gradients would be of the value between 0 and 1 most probably. So in that case, it would just make the final gradient that comes at this point, um, at weights over here, it would be just very negligible. So due to this long sequences, if your problem statement needs long sequences of data inputs here, then it would just start, the gradients would just start vanishing till they reach very old time step um, weights. So that is exploding vanishing gradient, and also exploding gradient if at any point the values of the weights start are reasonably high, the linear combinations or the 10H activations etc start getting big, and accumulatively they start to go to a very high range, which makes them not a numbers. So these are the few basic problems that exist with RNN, but we don't have to worry about it. We are here to implement a simple RNN right now. So how does it look like is, you have the cell, we want to implement it. So you first step is to calculate a hidden state of current time step, which is xt multiplied with a weight that is converting x into h dimensions. So x will have some representations of some n embed. So you have to transform that into h. Then h t minus 1 will have to be have some computation to get transformed into h, and we'll add some bias. Then y at this time step will be calculated. This is basically the logics that we want, with some weights that are transforming y, that are transforming h into y. ht will be used to calculate yt and adding a bias. So this is what we'll do. Let's start with it. So for implementations, we are not going to use any of the modules from PyTorch like NN dot embedding, NN dot linear, etc. We are just going to randomly initialize weights of the correct dimensions. So first thing is we'll need to take input this x1, which would be a batch of 4 samples of some time steps each, and that will have to be transformed into a representation of some dimensions, right? So embed xb, or rather let's say uh, embedding layer, or we'll just see embedding equals to torch dot randn. So input to this would be vocab size, or rather um, input to this would be, yeah, so because the integers in our xp are in the range 0 to vocab size -1, this would be 0 to 26 because our vocab size is 27. So we'll just tell them vocab size is input and embed is output. This would be our embedding layer, which would embed x. Then we'll have weight that is transforming x to h, this thing, and this thing will need to initialize. Weight x to h is it would be an embed by hidden dimension, then w h h, oh sorry, w h h would be toss dot randn. Now h would be of hidden dimension size already, so input fan in for this would be hidden dimension. Then we'll have bh, bias for this purpose would be, let's initialize biases with zeros so that at initialization they don't um, cause any trouble for the unit Gaussian shape of the activations basically. So this should be of the size hidden dimension, because all these elements in this sums are of dimension hidden dimension, so it will get hidden dimension number of biases and they will be broadcasted for proper addition. Another two weights we need to parameters we need to initialize is why, which would be and so this input would be hidden dimension and output would be, again I think we should keep it as hidden dimensions, uh, or vocab size, sorry, because this would help us generate the logits. These are the logits for a particular sample or at a particular time step. So logits would be of the size vocab size so that we can apply softmax or cross entropy on top of it. By dot zeros vocab size. So these would be all of our parameters. Let's define parameters as a list of embedding wxh, whh, bh, why, by. So these are our parameters. For in will turn on the requires grad true. So all the weights initialized. Now let's do a forward pass. So for forward pass, we'll need to initialize a h0 h0 with all the zeros to enter the first time step. So h would be basically torch dot zeros. Now the shape of it would be, second dimension would be hidden dimension. The first dimension would be, because we are taking um a batch of data, so 4 by time steps or whatever. So hidden dimension would have for each batch at each time step. So hidden dimension is shared. It would have at each time step, each sample in the batch would have one particular hidden representation. So we would have to initialize it with batch size by hidden dimension. Then okay, so we have initialized it, but before that, let's generate a batch of data and unpack the dimensions of X batch and time dimensions of. So based on this, we will have B by hidden dimension of zeros in H. Then next is we iterate for for each time step, because it's very straightforward. Like once you have initial hidden state initialized, you keep on iterating over each time step and keep doing the computations inside each cell. That's what we want to do. And we also will also need to store the logits at each time step, because here we are predicting the token at each step. Given input, what should be the next token or character, so we need to store the time step at each step as well. So let's initialize a empty list. So at each time step, what we are going to do is, first would be to calculate xt. Input would be, because this, you see, xb is of shape b by t, but input going into a time step of a cell, we want only one time step. So out of t we want only one. So we want xb indexed with for all batches at t time dimension and at all embedding dimension, or rather no, that's not needed. So this would give us b by 1 shape. Or instead, it would be better if we can do it like this: x embedded equals to embedding we call on xp. So we'll index the embeddings from for all the indices at xb. So this would become from b by t to b by t by n embed, because this is n embed, right? Now if you index here, so this would become b by n embed. So basically, if we are doing something like this, this is also equivalent to doing indexing like this, slicing and indexing like this. But if it was not direct indexing here at one particular column, it would have been like this, or some column dimension would be there. But since we are indexing at a particular column, it just squeezes off this dimension and it becomes b by n embed. So once we have our xt, we update, um, we have our old h, previous time step h initialized, so we update new time step, which is xt matrix multiplied with w xh. So this would be xt multiplied with w xh, which is b by n embed. W xh is n embed by hidden dimension, so it would give b by hidden dimension. This matrix multiply, then we would do h at w HH. So again, this is and hidden dimension size embedding B by hidden dimension. This is hidden dimension by hidden dimension. So it would become B by hidden dimension after matrix multiply, and we'll in the end add B H bias term. Once you have our so this basically would give us hidden dimensions for each element in the batch. So B by hidden dimension. Now, once we have a representation from first time step, we would need to calculate the logits, as in here. We have calculated this for the entire batch. Now we need to calculate the logits for the entire batch. So our YT would be, also one thing is, this is activation tan H on top of the all the linear combination. Here what happens is you have H matrix multiply with W H Y. So this is hidden dimension by vocab size. This is B by hidden dimension. So with batch matrix multiply, it will become B by vocab size plus the B bias of this. So this should become B by vocab size. Now we'll also have to, so this is B by vocab size. So when we are, ideally we want to add logits dot append YT, right? So in the end, logits, if we will print shape of logits, it will become a list of B by vocab size elements. List of T B by vocab size tensors. At each time step, we are appending. So basically, at each, imagine this like at each time step for each particular batch, we are getting the logits of shape vocab size. When one input goes in, the output would be one character. So one character would be sampled from the logit of a vocab size. Now, it is not just one sample going in. For the efficiency purposes, we are entering a batch of, let's say, 4 examples. So 4 examples going into a first time step. For each of those samples and time step 0, will generate different vocab size, length vectors, probabilities, logits for each of the sample in the batch, and those have to be stacked somehow to uh, give us a shape of B by T by vocab size, right? Because in the end, we want to calculate the loss, we want the logits to be of the similar shape as of targets. Targets is of B by T size shape, so this logits we want to be of B by T by vocab size. So what we do is return rather we stack each element in the logits list at dimension 1. So what happens is this would become of the shape B by T by vocab size. Now what we can do is, once we have the logits, Once we have the logits, we can calculate loss, which is f dot cross entropy. Sorry, cross entropy. Now logits and targets have to be sorry, YB have to be entered, but as we recalled, as if you remember from previous videos of GPT, these have to be of a particular shape to work with the cross entropy function in PyTorch. So we'll have to view them differently. So we'll have to have two dimension, out of which second is vocab size. So first it has to be guessed by its own, which should be b by t, or we can say -1. And yb dot view, there should be a single vector of all the integers in the batch. So basically -1, which would be b times t. And also there would be one more thing, if you remember, if you look back how we padded our sequences. So in the outputs we added padded sequence equals to 1 instead of 0. This was done so that loss calculation for these time steps would be ignored. That's why we did -1 there. So we can use that argument, ignore index equals to -1. So this would give us loss. We'll print loss dot item. Uh, so yeah, let's run it for too many indices for tensor of dimension 2. Let's print out shape 4 by 8 by 8, which is okay. 8 is the time step, and okay, so 7 time step and 8 hidden number of embedding it is indexing into. So basically it's saying that 1 by 4 times 1 times 4, 8 by 32. Okay, I think instead of xb it should be x embed. Then we'll able to index it like this. So this thing indexing that I've written right now is similar, exactly same as what this would do, but for explicitly showing it, will because we have 3 dimensions in x embed, so we'll index like this. Now okay, so now if you see, the loss is coming out to be 10, 11, etc, etc. So it's in the range of 9 to 12 ballpark, right? We are not training it now, we have just run one forward pass and calculated the loss on it. One thing is, as we saw in our very basic neural networks that we implemented, is that the initialization of the weight matrices is of very crucial importance to maintain the unit Gaussian shape at the initialization. But just with initializing it with torch.randn, due to a lot of matrix multiplication going on within the network, they explode. The variance or the standard deviation of the activations explode. So generally what we do is we scale them with some numbers. Now I'm randomly scaling them with 0.01. um, let's say 0.1 for this. So we have been seeing loss number of a high range. Now it should get to, yeah, Now this is constant around 3.29. Okay, so now we can put this to train. Um, we will define a hyperparameter max iteers. Let's say 1000. So for 1000 iterations, we'll run this, and we let's print the loss only when if iter percentage at every 100 time step, at every 100 interval, print loss dot item. Sorry, let's not print this now. Let's initialize it again, the weights again, and print the loss. Okay, so we are printing the loss, but we are not operating the weights, therefore it is coming out to be almost the same. Now what we should do is, after loss calculation, um, for p in parameters, we need to do grad equals to none for each of the parameters, and then call loss dot backward. Once we have loss dot backward, these p dot gradients for each weight should be calculated. Now we'll have to do parameters p dot data. We need to update them with some learning rate. So for now, let's say learning rate equals to 0.1 equals to minus of learning rate times p dot grad for that particular parameter. So once we have done this, the weights have updated. Now in the next iteration, it should print the lesser loss basically. All right, so let's do the initialization again and run it for 1000 iteration. All right, so we see that the loss is decreasing, although this is training loss, but yeah, we are training now. So let's quickly also bring in the generate functionality using these weights. So generate would look very much similar to what we were doing in our previous examples. So I'll just bring that code basically here. So I'm printing 5 names, initializing a 0 is initialized with this shape one by one because we are taking batch input into the model, into the weights, and then initializing a hidden dimension also because batch size is 1 now and hidden dimension. Um, so yeah, embedding index the last time step from our IDX because we want only one time step going at a time. So we take the last one at this point and then calculate hidden, update the hidden state, calculate the logits, calculate probabilities out of logits with softmax across last dimension, sample next index with toss.multinomial, append that next index with IDX. So the size of IDX keeps increasing, and so because next IDX that you get here is a tensor of, I think, rank 2, so we'll have to index twice inside this to get we'll have to because IDX is of rank 2 due to this initialization shape, so we'll have to make this of and wrap this into a tensor of rank 2, and then if this is the exit condition, if we at any point of time we output our network outputs 0 as the next index, we should exit and print that particular name. So yeah, let's try to generate now. So yeah, we are generating this. Let's say we have initialized a model and we have not trained it. So this is how the generations would look like. You see, it's totally gibberish. But now let's say if we train it for 1000 iterations, or let's say 2000 iterations, right? Cool. 2.0. So what the names would look like? Yeah, they look much better than the gibberish generation earlier. So yeah, this is what basically a single layer RNN looks like. This is a single layer. This is a single layer. What happens if you stack one layer on top of each other before getting to a final output that we calculate loss upon? Those would become multi-layer RNNs. Maybe I'll add that part and push into the GitHub link, or maybe I'll record a video for it. I'll see. But yeah, so this is how a single layer RNN works for a very simple token character level token examples. One character goes in, you one character comes out, so you calculate logits upon all of these. Yeah, so this was it. I'll do another video for LSTM, which is a slight modification upon improving upon all the shortcomings of the RNNs that we discussed earlier, which is very less reliance upon the old time steps history on generating tokens in the future because of vanishing gradients, exploding gradients, etc. So yeah, thank you.